So now it's my pleasure to introduce Marc Teichtahl from VersaTel.
Good afternoon, everybody. First of all, thank you to, can you hear me? Just a little bit more volume on the mic. Okay, yeah, is that better? Okay. First of all, just a thanks to Patrick Gilmore for the loan of his notebook, because I forgot to bring my port replicator for my bio, which was one of those things that you do. NANOG 16, I think it was, I presented part one of this presentation, which was our deployment plans for optimized packet rings deploying Cisco DPT or SRP technology. In that talk, we covered what we would like to do and how we would like to do it. We've come a long way since then. We've rolled out one of the rings. We're just about finished installing the core ring, OC48 core ring. So the talk today is to continue on from that talk and to look at some of the issues associated with our deployment, and also to look at some of the solutions. So we're going to focus a little bit on some of the issues we had mapping things like fiber topologies into ring topologies, how we did that. We're going to look at IGP issues and EGP issues as well, how we actually configured our routing. It's actually quite a complex exercise in the structure that we have. So part one of the first presentation I did at NANOG 16, the brief was basically to effect the migration from traditional transmission technologies to a next generation platform optimized for the transmission of purely packetized data. Now I'm sure all of you out there understand why this is an important thing to do. We've even touched on some of the issues today with MPLS and some of those discussions. So this was a design brief. Taking this brief from my management, we went away and we did the design for these rings. Why we were asked to do it? Obviously, it's a cool thing to do, but more importantly is the money associated with it. So the general business drivers, not just for us as a company, but for all organizations that are looking to do this, is to move into a structure where you can provide all your services based over an IP infrastructure. In many ways, this reduces costs and can actually increase your revenue. Therefore, obviously, you become more profitable. It also provides with a single management platform. You no longer need to manage your ADMs as well as your IP routers. You can use a single management platform. So that provides you ease of ongoing operations and support, and also, with certain regards as well, lower maintenance costs and cost of ownership. Also, business drivers is also to lead the push into IP optics, layer 2 and layer 3 signaling and things like that, and also to have the opportunity to influence the early adopters in the marketplace, to get in there early with these type of technologies. Specifically for VersaTel as a company, we're a fiber carrier, a facilities-based fiber carrier in the Benelux region and now also northwest Germany. For us, it was actually to better utilize our fiber network. Also, one of the challenges from our management was to map the fiber technology against a decent network architecture which could be utilized as a profitable product, to decrease the cost per megabit per second on the network, to shorten provisioning lead time so we could provision more customers faster and more accurately. Also shorten the product time to market. With these facilities, you don't need to provision circuits that need to go into your SDH guys or your switch ops guys. It can all be done by your IP guys in one centralized team. Provide endless scalability. I know we hear endless a lot. If we look towards new technologies, that's becoming not necessarily a reality, but becoming something we need to consider. How do we provide endless scalability for the backbone and for customers? To provide a DWDM plug-and-play model where what we develop today is sort of a step one towards a full DWDM solution in our network, where we can pick up the current network and plonk it onto lambdas, for example. And also to provide forward consideration to MPLS and multi-protocol lambda switching. So this is just a little graph here, just done off the top of my head. Figures possibly fictitious, but I think in the realms of reality for what we could actually expect when we look to these type of technologies in our network. The left-hand scale is basically a list of products. Where we are today, we're sort of into things like WAN carriage over SDH and things like that. Really, we should be heading towards providing IP-based circuits, which is at the top of the scale there, and obviously that's at the top end of the technology push, as well as the maximum revenue and profit area as well. So we're really trying to climb this technology curve to maximise a return on investment as soon as possible. If anybody has any questions, I think we can take them as we go along rather than at the end, because this actually jumps between some very different areas. So if you have questions, just come up to a mic and I'll take them as we go along. So our challenges as a fibre provider in the Benelux area, which is Belgium, Luxembourg and the Netherlands, was mapping the technology. That was both mapping technology onto fibre infrastructure and mapping technology for products and mapping technologies to business plans for CapEx and expenditure and things like that as well. Also matching segment parameters. The distances in this area are quite small. Our longest segment is about 200 kilometres. I'm not going to convert that to miles because it's too hard, but about 200 kilometres. That gives us, I think in the US you would probably term that more of a metropolitan type of network, but that's for us that's an international network. So we had some issues in how we actually match these segments and how do we actually overlay the optical infrastructure over these type of distances. So that was quite challenging. I covered that in some depth as well. And associated with that is how did we design optical regeneration? Once we had actually matched the topologies, how did we do the optical regeneration? Obviously we don't want to have SDH in this network, and later on in the presentation I touch on how we actually did the comparison and made the decision not to implement any SDH in this network. There are SRP overhead considerations as well we needed to look at. Also, where do we actually choose to build our pots along this fibre? Do we build it based according to where we need to put optical regens? Do we do it based on where we can generate maximum revenue from the products we sell? So there are a whole range of questions we needed to address there as well. And then once we did this, how did we actually fit all the rings together? We're actually going to be building 9 rings. So how do we actually join these rings together? And that's both an IP and a fibre, sort of a layer 1, layer 2, layer 3 issue, if you wanted to go that far. So to SDH or not to SDH, or you guys call it SONET here, so this is more tailored for a European market, but SDH provides us with circuit capacity, real circuit capacity on our fibre network. DPT or SRP technology does not allow us to define customer-based circuits, but single pipes based on pure IP capacity. So with this in mind, how does this impact our business model? This was actually a major stumbling block in our organisation as we looked into how we did this project. One of the issues is as you sell IP, you generally like to sell it cheaper for the same amount of capacity. So your revenues actually do decrease when you sell these products compared to a SONET solution. Generally, IP is cheaper. And it is also cheaper to implement DPT. So there's a trade-off there between revenues and the cost of implementation, and that becomes a strategic decision within your organisation. So based on these two facts, then the key factor for financial success is that we need to do higher volume sales, which obviously the maths there is quite simple to figure that one out. So to be more profitable, we need to sell more of these IP-based products, higher volumes. The thing with SDH in this type of architecture is that it will always have a higher incremental cost as you build your network, because you must implement, first of all, the fibre, and then you must terminate it on an ADM, and then you must add the router, which still has your DPT line card in it, for example. So you always have to add the router. SDH or SONET will yield a broader range of more profitable products. And DPT is obviously, it's optimized purely for IP. So, I mean, these were the considerations that we had to think about as we were deploying the network. And we traded them off and we decided that we're going to go the DPT route. We also thought that we may have to utilize SONET or SDH in some segments in our rings due to the optical path, length, and also the fibre requirements to close the rings. For those of you who've done ring architecture design before, it's very possible for a small ring to have to traverse large amounts of fibre to close it over the redundant path. So we had some fibre costs, metrics associated with our decisions as well in terms of the architecture of the network. Any questions so far? Because it's going to make a bit of a quantum jump. Okay. So we had basically 6 problems when we had to look at the topology of this network. We had to build 9 fiber rings covering 35 POPs in 3 countries. That's actually now expanded to 4. Geographical distances and optical limitations were a huge problem for us, as well as traffic distribution and the line card issues we saw with the Cisco DPT line cards. So the solution that we came up with was to create an international core ring at OC48 speeds. There was some duplication of fiber paths in this design, which you'll see in a moment, but there was actually a specific reason for doing that. So we decided we'd build an international core ring, and we would actually overlay onto that local distribution rings per country or per region as we define them. And we had to utilize optical regeneration. So we chose not to go with the Sonnet solution and ADMs on the longer paths. We decided to go with optical regeneration. Of course, this is only sensible if you own the fiber in the ground. You're not going to get your telco here to do that over large distances. But for us being a major carrier, this was quite a sensible solution in terms of scalability and growth, because we can just pop those out, wrap the ring, install a new optical regen at the higher speeds. So this was a sensible solution for us. So without going into too much detail about this map, basically we build a 6-POP core ring, OC48 speeds, with 1, 2, 3, I think it's 7 or 8 distribution rings that hang off it. Before I touch on the issue of having to close over longer paths, I'll pull up a slide now that shows, damn, it didn't come up too well. Basically, hang on. This ring is more of a logical diagram. For us to actually close, especially one of these northern rings, we had to, it was open along the top of the ring, but to close it, we had to still close it across the entire core ring. So in actual fact, to actually make this work, we're actually using 10 pairs of fiber. And that's actually quite an expensive thing to be doing on an international network. So there are actually 10 pairs of fiber being used to close the rings to provide the redundancy. So you can actually imagine if we had to purchase that fiber from somebody else, the actual cost involved to do that would be tremendous. Unfortunately, this didn't come out as well, but this outlays optical path loss on the network as well as where we've decided to place the regenerators. In some places, we've chosen to build a POP, point of presence, where we need to optically regenerate. In other places, we've decided to splice the fiber, cut the fiber open, and actually put the optical regen in. It's a shame this slide didn't come out more, because I wanted to cover some more issues, but I'll come back to these a little later. I touched on line card limitations too before in our challenges. One of the issues is it is proprietary to Cisco. I understand from my discussions with Cisco that it is being taken to the IETF for standards ratification. The indications I've been given that it should be about 2 years before we see an open standard for SRP/DPT technology come out. And there are a whole broad range of issues I'm not going to touch on, but there are some documentation online that I can point you towards later. Line card limitations in terms of optical path length. We're limited to 25 dB loss on any path. We're currently limited to OC48 is the maximum speed that we can utilize. We're also limited to 32 SRP nodes per ring. And on the GSR 12016, 1212, and 12008, the actual slot capacity as we get higher into the OC48 and OC192 cards, OC48 requires 2 slots. So we're going to start to see these, if you think back to the other one, in some of the POPs, we're actually going to have 3 or 4 routers to connect the rings. We're starting to chew up a lot of slots just terminating these DPT rings. Matching the segment parameters was actually one of the trickiest things we did. Each optical segment between the POPs or between the optical regenerators had to be within the optical tolerance of all the components in the network. And that would be not just the Cisco products, but anything else that we wanted to put in there in the future. So that was quite a challenge to look into the future as well and say, okay, well, if it's going to take 2 years to ratify the standards, what's Juniper doing? What are the other vendors doing? Are we going to see new technology coming out? For example, I believe the 6500 switches are looking at building in some DPT cards for those. So, what are the design parameters for those? Where can we use them? Can we drop them directly in an office on one of these distribution rings, for example, and supply voice and data off the same switch? So there are a lot of things we had to think about as we were designing that. So basically, we did achieve matching the segments just by using optical regenerators. Where are we? Yeah, we did consider, and seriously consider on some paths, especially the longer paths, to close the rings to utilize Sonnet SDH. I should have written SONET there, I'm sorry. SDH. We didn't use it due to capacity constraints. As we scale the IP network, we expect that to scale a lot faster than our traditional ADM SONET SDH network. And we didn't want to be tied to what the SONET rings were being scaled to, so we decided not to use it on a lot of all of the segments. And it's also not as plug and playable as a purely optical solution where we can just go in, rip regens out, change line cards, wrap the rings where we need it. As well as that, I didn't put it here, but we actually also rely on another team within the organisation, which I'm sure many of you would, to actually go and configure the circuits, etc. Optical regenerators, again, based upon the tolerances of SRP line cards, maximum loss of 25 dB, like I said before, the maximum path length is 80 kilometres. As I said before, our longest segment is about 200 or thereabouts, so that's obviously going to require at least 2 regens. So this was achievable due to physical fibre paths and the ability to easily splice when needed. And again, that's an advantage we have just in where we are in the marketplace. That's not always an advantage. So SDH may be an alternative for those of you looking to implement this in your own environment. Overhead considerations. I had an interesting question from one of the guys, one of our SONET guys, who said, well, what's the overhead as we grow this network? What's the IPS overhead? What's the SRP overhead? How does all that work? Are we going to see impacts if we scale this up to hundreds of nodes? I wasn't actually sure. I had to go and do some research to find out the answer to this. Basically what I found out in regards to overhead is that the IPS packets, intelligent protection switching packets, only travel between adjacent nodes. So immediately I could eliminate that as a huge issue because they're quite small. I was concerned about the topology discovery messages. To actually understand its own topology, the SRP protocol will transmit around the ring the topology packets which outlay the architecture or the topology of the network. They're natively 32 bytes, and every additional node you add to the network adds an additional 8 bytes per node, and they're sent every 5 seconds around the ring. So if I look at a nominal ring size of 10 nodes, that's about 1.5K a second for IPS. And obviously on an OC48 ring, who cares? It's absolutely negligible. But when I look at the other protocols used on the ring, we have IPS, topology discovery, and usage control. For 10 nodes, we calculate to be roughly, at OC48 speeds, 2 megabits a second. So again, relatively negligible. And just a little calculation here at OC12, the ring overhead is less than 1%. So we saw no issue there with overhead. Just a little graph showing overhead parameters here as you go up to 32 nodes per ring, and this is inter-node traffic. This is not across the whole ring. So it's very small. I should have done it in percentage of the actual capacity between the nodes. I think would have been more useful. But nevertheless, it's very small. Before I touch pop selection, there is one thing I forgot to add. As we deployed this, we did see quite a few bugs in the Cisco code, especially in 12.05 S1, I think it was. Interesting problem. I'll tell you about it. We built the ring, everything's running properly, the ISIS was running, the BGP was running, there were no problems, except the topology database was completely incorrect. And funnily enough, when we looked at it and we followed the discovery messages as they were flying around the network, we found out that they were being shifted 4 octets to the right every time it went through a node. Funnily enough, the rings worked, there was no issue at all, except the topology was broken, the databases were broken, and we had some concerns that as we look towards MPLS and things like that may cause us concerns in the future. So there is actually now a bug being fixed by Cisco for that one at the moment. Okay, pop selection. On this architecture, how do we actually choose our points of presence? We base them on 2 criteria, return on investment. Where do we build the POP to get the most return on investment? Obviously, it's quite an expensive exercise to be laying this out. Like I said before, it's 10 fibres around the ring, basically. 10 pairs of fibre around the ring, and multi-millions in equipment. So how do we actually maximise it? Well, you want to get your POPs as close to, say, business parks, exchange points and things like that, where you can actually sell your services into these facilities. And again, if you want to do that, that impacts your path selection in terms of mapping the actual logical network onto the topology, because it may actually pull you out of the way to get close to these places. So we actually We let the commercial guys tell us where to put the POPs, strangely enough, because they're the guys who give us money. Optical distances, of course, is a consideration, and again, like I said, proximity to interesting sites such as exchange points, possible major customers, developing business parks, etc. Okay, now, the International Core Ring. It's an OC48 International Core Ring. It's based on Cisco 12016s. It's covering 625 miles. It only utilizes 5 optical regions. The minimum optical loss we see is 4.2 dB, and the maximum we see is 24.2 dB, which is just borderline. So again, we have to be on top of the technology to make sure that whatever we do upgrade, that the tolerances, that we actually understand the tolerances on each segment as we incorporate new equipment into the architecture. The local distribution rings are OC12 based. There are 8 distribution rings. They're based on Cisco 12008s. They're covering roughly 1,875 route miles. They're utilizing 19 optical regenerators. The SRP interconnect issues. At the major points where the distribution rings cross the core ring, we require an interconnect methodology that allows for the overlay of complex routing architecture, so we can get optimal routing between the distribution rings and the core rings. So that touches on things like summarization, confederations, route reflectors, which I'll touch on in a moment. But basically from this diagram, the core POPs will each have, these are actually physically different points of presence. I didn't show that clearly on this diagram, but these are different points of presence. So the 1216s will bring in the OC48 core ring. The 1208s, pardon me, will bring in the OC12 distribution rings, and they will both come together on the 1216s. So the reason for actually bringing these in different POPs was that if we do lose a POP, the ring will still operate. We didn't want to close into one POP, so we actually closed rings through 2 POPs. And I'll jump back to the architecture to highlight that. It's quite an important design feature. So you can see here that each ring is always closed. Say, for example, this ring here, even though it's more of a rectangle, but it is a ring, closes through Rotterdam in a place called Sloterdijk, which is in Amsterdam. The Belgian ring, the southern ring, is closed through Brussels and Antwerp. So the whole methodology behind that was if we do lose the Brussels POP for whatever reason, that the ring will still operate through Antwerp. You still get traffic around without any major issues. Of course, the 12008s also provide ingress and egress for the distribution POPs. The distribution of traffic into POPs as well, which I'll cover on in the POP architecture in a moment. At the moment, under high volume, there are unknown inter-ring SRP issues. We're not carrying gigabits of capacity yet. We will, but we're not. So we don't know under high volumes how this is going to perform. That's an unknown at this point in time. Statistically, there is a possibility of a runaway restore condition when both rings wrap at the same time. So if we look at this architecture, if the rings were to wrap at the same time, DPT provides for 50 millisecond healing. If they both wrap at the same time, it's possible we'll get a stalemate condition and things will break. This is yet to be proven, and if anybody wants to get into a lab with me and try it, I'd be more than happy to work with somebody to do that. Because I think that's quite interesting when you join these rings together. What are the possibilities of these runaway conditions? Oh, going the wrong way. Inter-ring IPS overhead issues as well. Again, they're just between the nodes, but we don't know how that performs again under load or under those runaway conditions between the core and the distribution ring. So that needs to be tested further as well. And again, will we see under high load serialization issues or delay issues as we bring traffic between the rings? We're running a fully loaded OC48 ring, for example, or at least not necessarily even fully loaded, but more than an OC12 with the capacity coming towards one ring, which unfortunately the way our IP services are laid out in our region of the world, it's actually possible for that to happen theoretically. Will we see serialization delay issues, any of those issues? We don't know. All these issues really, to us, are things that we're going to learn in the future as we increase the volumes in the network. And then it comes to the routing issues. How do we actually make these 8 rings and 1 core ring, bring them all together, route we've made use of a single per POP border router, which is responsible for all our external eBGP connections for transit providers. Although that's not true for eBGP sessions to customers, that's handled on a customer attached router. We utilize ISIS and BGP, obviously. Again, will there be impact of the overhead, and also what are the comparisons if we were to route this over an SDH setup? So, unfortunately, I couldn't get this Visio to work properly. Don't ask me why. All the other diagrams work but this one. So, this is basically a POP architecture. These are the 12. These are 12008. This is the OC12 distribution ring. All the connects are GIGI interconnects between the routers. These are 7507s. These are 7513s. These are 6509s, and these are generally banks of 6 to 12 RAS servers. We have various vendors in our network. So this is our standard POP design, which is implemented in all POPs. So the actual designation for the routers in this POP design, each POP has a border router where we take transit from other providers. Connection to the distribution routers, the reason they're connected to the distribution routers and not further inside the POP architecture is speed of transport between POPs in the event of failure. We don't take redundant connections from upstream providers in the same POP. We'll take them in two different POPs. The theory is that we have enough capacity between the POPs on the ring to carry the traffic should we lose one of the links. It also provides us with a small amount of lower cost, not significant, but it is quite small in terms of our business concept to implement this. I've got no idea why I wrote multiple full tables. I guess the router takes multiple full tables. I've got no idea why that's there. ISIS, each POP has a designated net identifier. All inter-POPs, so all the routes within the POPs are kept as level 1, for those of you who know ISIS. All intra-POP and core distribution routes are summarized on POP border routers and distributed into the distribution of the core rings level 2 summary routes. For the dial POPs, SuperNets are summarized at the dial aggregation 6509s, and they're sent into the POP at level 2. This causes some trouble, which I'll touch on in a moment, and only the core carries only level 2 summary routes, so we're trying to keep the number of routes traveling around the core ring as low as possible. ISIS issues. One of the biggest issues we had was summarization is only allowed at the border between two levels, between level 1 and level 2, which means that, say, for example, we brought in a 16 or a 19 for dial in a POP. They'll be presented via ISIS to the 6509s as /32s. Obviously, I don't want those in my core, so I need to summarize those. The only way I could do that was to summarize them into a level 2 route. Obviously, that breaks when I want to further summarize those to bring them from different POPs in the distribution ring as a single announcement, as say a 15, for example. Luckily, in 12.0 and up, there is a nice command that allows me to regress the level back 1, so I could bring them into level 2 across the level border, and then bring it back to level 1, and then bring them back forward again as a level 2 into the distribution or the core ring. Without that command, we would have some issues there. For us, integration with our legacy OSPF network may still prove to be an issue in the future. We haven't integrated the old network and the new network yet. That's currently under design, but we are considering some possible issues with the OSPF. We've also found that we're having some issues with the lack of flexibility in route selection and metric preferences. Now, that could be we just want too much from the protocol, or we haven't actually thought about it well enough, but we're seeing some issues there as well. Although the benefits are quite good, easy configuration, simple adaptation for MPLS when the extensions come out. Convergence speeds are very good in the network for the IGP. And it provides us also very good flexibility in our naming schemes for the POPs when we allocate net names to each POP. Okay, I'll talk quickly now, see if we can get through the slides. All POP border and customer aggregation routers are BGP speakers. We utilize a full meshes between the POPs, and each POP is a confederation by itself. And we do use route reflectors within the POPs to provide redundancy. We provide one active path and one backup path for every route in the network. So we use route reflectors to actually do that between the forward path, the primary path and the backup path. Again, my Visio died, so that diagram's not in there. Future visions. What are we aiming to do in the future? Why did we do this today? We're looking towards utilising both IP layer and optical layer MPLS signalling. We aim to provide intelligent IP lambda capacity. Basically, we want to, in the future, provide the ability for our customers to request optical capacity through the IP layer. So should they buy a chunk of capacity from us, they may choose to switch in more capacity through the IP layer, talking to the optical layer. And also, should we run out of optical capacity on any path, to reroute that capacity via IP. Migration of dark fiber to an intelligent DWDM solution. One of the possibilities there is to provide lambdas for customer distribution rings hanging off our distribution rings for customers who want to have multiple offices in business parks, etc. And to provide intelligent optical switching, I guess, is really the key feature we're looking for, optical path selection and reroute both optically and IP. And that is the end. So if there are any questions, I'll be happy to take those. I guess I bored you all to death. Okay, thank you.